Assalamu alaikum wa rahmatullahi wa barakatuh. This is the last video in chapter 8 in Newton's laws, but it's just about tips and hints. In this video, we are not going to give you new objectives about the lesson, but new hints that will help you analyze different situations in real life and answer some questions that you may be asked. We are going to talk about the effect of launching positions, the effect of frame of reference, the effect of the initial velocity v0, and the angle alpha, finally the horizontal launching. Starting with the effect of launching positions, I'm going to present two different situations and we are going to compare them to make our study. Suppose that a particle is shot from a height h1 above ground with initial velocity v0. That is making an angle alpha with the horizontal. The particle will move in the plane, then reaches a maximum height position, then it falls finally down on the ground at a point, let's name it as A. The same shot with the same initial velocity will be repeated. The particle is launched now from a height h2 above ground and it is higher than the first one. Same as the first case, the particle will move in the plane, reach its maximum position, then falls down again on the ground at a point, let's name it as B. Putting the two situations side by side, we can think together to see if there is a real effect of the chosen initial position. First question, what can you say about the range? Would it be affected by the change of the launching position? Let's check it. The range is the horizontal distance at the same level of the initial launching position. The second case, also the same definition, the range is the horizontal distance at the same level of the initial launching position. Is there any change in the range? Increase, decrease, or it's the same? It's clear that it's the same. Now what about the maximum height? Let's check it. We measure it as the maximum height reached by the particle after the moment of launching it. Then it is the same. Excellent. Now the maximum height above ground is just the maximum height reached by the particle plus the height h1 or h2 according to the case. It differs and it increases. Finally, let's check the horizontal distance traveled to reach the ground D. So the first one reaches point A, the second one reaches point B. This difference in the distance is clear and it increases. We deduce then that if there is a difference in the launching position as a height, there is no change in the range or the maximum height, but it differs in the maximum height above ground and the horizontal distance. As the launching position is higher, the distance on the ground will be greater. Now the second study is related to the chosen frame of reference. This time we fix the initial height and the initial velocity in a way that we are going to have a range R, a maximum height h maximum, and finally h maximum above ground as they are represented on the figure. Now first we are going to choose the frame of reference such that the horizontal x-axis is passing through the point of launching, which is at a height h. On another case, we're going to consider a frame of reference such that x-axis is passing through the ground. Now we are going to see if the chosen of the frame of reference will affect on the range, the height maximum above ground, and the horizontal distance. Think of it and let's check the answer. It's clear that when we draw the first frame of reference and then the second frame of reference, none of what are represented on the graph changed. We have same range, same maximum height, same maximum height above ground, and the same horizontal distance traveled to reach the ground D. How can we prove this? By calculations. We are going to represent their expressions in the two frame of reference, such that the equation of trajectory y equals to f of x is given as minus g over 2 into v0 cosine alpha squared times x squared plus tangent alpha x if we are considering the first frame. Considering the second frame, we are going to add y0, which is the height h. Considering the range, the expression of range is v0 squared over g sine 2 alpha, nothing related to the initial position or the frame of reference. So it's the same. The height maximum is given as v0 squared over g sine squared alpha over 2. It is not affected by the chosen frame of reference, then it is the same. Now h maximum above ground, in both cases we're going to add the maximum height reached by the particle with the initial height h, then it's the same. Now distance O to B. In both cases it's the same. Since we are considering the distance in the ground, also it's not related to the chosen frame of reference. Finally, the y maximum, the maximum position reached by the particle, we calculate it going back to the equation of trajectory. So in the first case, it will give us h maximum, while using the equation of trajectory in the second frame of reference, we will get the maximum height above ground. So in this case, it will differ by calculation. Finally, we can say that the range and the maximum height are not affected by the change of initial position or the launching position. Now, the effect of initial velocity and the angle of launching alpha. Let's consider the situation where we have a particle launched with initial velocity v01, making an angle alpha. It reaches point A. Now, what if we keep the angle alpha, but we increase the initial velocity by v02? Will the range and maximum height differ? Think of it and tell me. If we increase the initial velocity, this particle will reach a point B farther than A. We can see then that the range differs, the maximum height also increases. How can we prove this using their expressions? The range is expressed by v0 squared over g sine 2 alpha. Then it depends on the initial velocity and the angle alpha. The h maximum is v0 squared over g, the same factor in the range, but times sine square alpha over 2. Here we can see that both are proportional to v0 squared, so they increase with the increase of v0. Let's see the effect of alpha. Now suppose that initially we launch a particle with initial velocity v0 making angle 15 degrees with the horizontal. Now we're going to increase the angle keeping the same initial velocity. The third example. Great. Now we can check the different values of alpha. 15 degrees, 30 degrees, and 45 degrees, and compare the range covered by the particle in each situation. What if we keep increasing the angle alpha? Let's choose the angle 60, then 75 degrees. We can see that the range is decreasing. It's clear that the range increases till it reaches a given range. After that, it starts to decrease. Then we say that the range increases if alpha increases when it is between 0 and 45 degrees. while at 45 degrees it is the maximum range reached by the particle. Then the range decreases if alpha increases between 45 degrees and 90 degrees. What about H maximum? According to H maximum, it always increases as alpha increases. But be aware that with the same initial velocity, complementary angles have same range. Like what? Like launching it with the angle 15 and the angle of 75 degrees. 15 plus 75 is 90 degrees, and both have the same range. What about 30 and 60? The same. 30 plus 60 is 90, and both have the same range. The horizontal launching. The horizontal launching is expressed when the particle is launched with an angle alpha equals to 0 with the horizontal. In this case, the trajectory is directed directly downward. So instead of choosing the frame of reference where x to the right with the direction of motion and y is upward, we choose it downward since the whole motion is downward. In this case, if we are going to choose the initial conditions, they are 0 and 0 for x and y, while v0 vector can be found by replacing the angle 0 in the vector that we have taken in the oblique launching, and we are getting the values v0x as just v0, and it's clear from the figure v0y is 0 since there is no initial velocity along y. What about the gravitational acceleration? It is all the time directed downward. In this case, the y-axis and the g-vector are of same direction. So writing the components of a vector or g vector is 0 plus g, not minus g. After that, we find v vector by antiderivative, and it is v0 I vector plus gt j vector. Since v0 is v0x at any time and v0y is 0. By antiderivative, r vector is v0t I plus g over 2 t squared. There is no v0y and there is no y0, there is no x0. The equation of trajectory is taken as g over 2v0 cosine alpha, all of it squared, x squared, if we are considering the general equation in the last video. Replacing alpha by 0, this expression becomes g x squared over 2v0 squared. The range now is 0 since we can replace alpha by 0 and sine alpha is 0, so it is 0. Note that from the figure, it's clear that the particle didn't reach a horizontal level symmetric to O, so there is no range. The maximum height, which is v0 squared over g sine squared alpha over 2, also is 0 since sine alpha is 0. It is good to solve this application. A basket player throws a ball with a velocity v0 vector from a height equal to that of the basket and scored. The throw is considered a free fall and the launching angle is 55 degrees. The range is 3 meters. Given the expression of the velocity vector at any time and the expression of the range. The first question: calculate the initial speed of the ball. Now they gave us the expression of v, but we don't have exactly v0. We try to use the expression of the range since range depends on v0. Now, r equals to v0 squared over g sine 2 alpha. Then, initially, alpha is 55 degrees. We can replace alpha by 55 degrees, g by 9.8, r by 3 meters, and finally v0 is 5.6 meters per second approximately. The second part, calculate the time of ascending phase of the ball. Then it needs the time taken by the ball to reach the maximum from O to A. We know that it is the time taken to reach the maximum height. Then we can compute it by using Vy equals to 0. Now Vy, which is minus gt OA plus V0 sine alpha, is 0. Replace alpha, V0 that we have just found, G, then this time is 0.47 seconds. Justify that the time taken by the ball from highest position to reach the initial level is the same as that of the ascending phase. So we need to find the time taken from O to A, then from A to B. The time from O to B is TOA plus TAB. And we know that the speed along x-axis is constant. Then let's use V0x, which is OB over TOB, where TOB is OB over V0x equals to the range over V0 cosine alpha. OB is the range and V0x is V0 cosine alpha. Replace R, V0, alpha by their values. We get that TOB is 0.935 seconds. Therefore, to find the time from A to B, we can subtract the time TOA from TOB, and the result is 0.47 approximately, which is equal to that taken by the ball to reach A from O. Knowing that the 2 points on the same level on the parabola have the same speed, verify that V0 is equal to V at point B. The velocity at point B is tangent to the trajectory at point B, and it is oblique. Therefore, we can make its projections along X and along Y. We're going to find their values, then find the magnitude at B and compare it with the initial velocity at O. The velocity at O is V0 and it's found to be 5.6 meters per second. The X component of the velocity at B is V0 cosine alpha, and it's just 3.208 meters per second. The Y component is minus G T from O to B plus V0 sine alpha, the initial value. It is minus 4.576 meters per second. Now VB is the radical of the X component squared plus the Y component squared. By calculation, it is 5.6 meters per second approximately. The last part, deduce that the angle beta between VB vector and OX is also equal to the launching angle alpha, which is 55 degrees. In order to find this, check the projections along X and along Y. This angle beta is equal to the angle between VB and Vx of B. Then, we can use tangent beta, which is equal to the opposite, which is Vyb in absolute value, of course, over Vxb. It is 1.426. Then, beta is 55 degrees. Therefore, alpha and beta are equal to each other. This is the end of part 7. Hope these hints or tips will help you in analyzing any problem. Study well and thank you for watching.